Let's talk about a question that sits at the very heart of engineering, a puzzle that shapes everything from the phone in your hand to the bridges you drive across. How do you pick the absolute right material for the job? It sounds simple, right? But as you're about to see, getting it right is anything but.
So, let me ask you, what's the best material? If you're designing a new airplane wing, what's your first instinct? You'd probably say, well, the strongest one, of course, or maybe the lightest. That's going to save a ton of fuel. And you know what? Those are great starting points, but they're just one piece of a much, much bigger puzzle. Because in the real world of engineering, asking for the single best material is kind of like a trick question. You're always, and I mean always, juggling. You're trying to balance maximum strength against minimum cost against the lowest possible weight. And here's the kicker. You can almost never have it all.
And that brings us to the most important concept we're going to talk about today, the great engineering trade-off. Choosing a material isn't about finding perfection. It's an art form. It's the art of the perfect compromise.
This right here, this visualizes the whole problem perfectly. Think of your final design sitting in the middle of a constant tug of war. Pulling on one side are the material's properties. Is it strong? Is it stiff? Pulling on another side are the manufacturing processes. How do we actually make this thing? And from the third corner, you've got its function. What does this part need to do? The sweet spot, the right choice, is always found right there in the middle.
The source material really nails it here. It's incredibly rare to find a material that does everything you want perfectly. So you have to trade one characteristic for another. The classic example is strength versus ductility. Think about a paperclip. It's ductile, you can bend it and it holds its new shape. Now think about a glass rod. It's strong, but if you try to bend it, it just snaps. That choice, that trade-off, is something engineers think about constantly.
And these trade-offs are everywhere. You've got strength versus toughness. Do you want something that won't bend, or something that can take a huge hit without shattering? There's the endless battle of weight versus performance, which is the entire game in anything that flies or drives fast. And of course, the one we all understand, cost versus performance. That super amazing, lightweight, ultra-strong material? Yeah, it's almost definitely going to cost you.
And check this out. This graph shows that strength versus toughness idea beautifully. See metal A? The line goes way, way up. That means it's super strong. But then, poof, it just breaks. It's brittle. Now look at metal B. It doesn't reach the same peak strength, but look how far it stretches and deforms before it finally gives up. That entire area under the curve? That's its toughness. It absorbs energy. So think about a car bumper. You don't want the strongest material, you want the toughest.
Okay, so you have to make a choice, a compromise. But what are you choosing from? Let's do a quick run-through of the main material families, the main players in this game.
First up, you've got the workhorses, metals. We're talking steel, aluminum, titanium. They're strong, they're stiff, and they're usually ductile, meaning they bend before they break. So what's the catch? Well, they can be heavy, and a lot of them, well, they rust. Next, we've got polymers, what most of us just call plastics. These are amazing because they're light, they don't corrode, and you can mold them into all sorts of complex shapes for cheap. The trade-off? Generally, they're not as strong as metals, and they can get soft or melt when things get too hot. Then you have ceramics. These things are incredibly hard, super stiff, and fantastic when you need to handle high temperatures or a lot of wear and tear. But they have one huge weakness. They're brittle, just like a coffee mug. They don't bend, they just shatter. And finally, we have composites. This is where engineers get really creative and try to have the best of both worlds by combining different materials. Think carbon fiber. You get these incredible custom-made properties, like an insane strength-to-weight ratio. The big trade-offs? Oh yeah, they're usually really expensive and a lot trickier to make and repair. So, we have our big four families: metals, polymers, ceramics, and composites. But just knowing the lineup is only half the story. Now comes the hard part. How do you actually pick one for a real-world job? This is where it gets interesting. Because the right material completely depends on the context. Just look at the difference between making a car and making an airplane. In a car, you're fighting to cut every last gram to improve fuel economy, but at the end of the day, cost is king. In aerospace, performance and safety are everything. You'll happily use a super expensive titanium alloy because failure is simply not an option. Cost matters, but it takes a backseat to making sure that plane stays in the air.
Let's bring it down to a really simple example: water pipes in your house. On paper, steel is stronger, and the material itself is cheaper per foot. So that's the obvious choice, right? Well, not so fast. Copper is weaker, but it's also flexible. A plumber can bend it around corners super easily. That means less time, less labor, and fewer fittings. Plus, it's way more resistant to corrosion. So even though the copper material costs more upfront, the total cost to get it installed and keep it working for decades might actually be lower.
Or look at something we all know, a bicycle. It's a perfect case study in trade-offs. The forks have to soak up bumps, so you need toughness, that's why they use steel tubing. The wheels need to be light but stiff, so that's a job for an aluminum alloy. And the crankset, the part that takes all the force from your pedaling, that needs a special high-strength steel alloy so it doesn't bend or break. Every single part is its own little engineering problem with its own unique material solution.
So as you can see, engineering design is really all about this intricate balancing act. It's a dance of compromise. But what does the future of that dance look like?
Well, for one thing, the challenge is getting way bigger. Right now, engineers have over 100,000 different materials to pick from. To put that in perspective, that is a staggering number of choices. So how can any single person, or even a team, possibly weigh all the pros and cons for every single one of those options? It's a huge challenge, but it's also where the real innovation happens. And this is where things are really starting to change. We're seeing the rise of AI as a sort of co-pilot for engineers. Imagine an AI that can sift through all 100,000 of those materials in seconds, juggling every single variable. Strength, cost, weight, environmental impact, you name it. It could suggest solutions a human might never even think of, finding that perfect needle-in-a-haystack compromise. So I want to leave you with this final thought. As these incredibly powerful AI tools help us navigate this ocean of trade-offs, will we ever find the one perfect material? Or is it that clever, creative, and totally necessary art of compromise that will always be the true soul of engineering? Let me know what you think. Thanks for joining me.